Greetings, friends. It is my great pleasure to be able to lead you through a collective series of statements to establish a definite proposition. That is, the chain rule. The chain rule states that the derivative with respect to the derivative with respect to x of f of g of x is equal to the derivative of f with respect to g multiplied by the derivative of g with respect to x. Alternately framed with this notation, the derivative of the composition of f and g of x is f prime of g of x times f prime times g prime of x. Again, just the derivative of f with respect to g times the derivative of g with respect to x. So let's see what we know and what we're trying to prove. So this is what the beginning and the end of our proof will look like. So first we know that f of x and g of x are both differentiable, meaning that we can, if it suits our needs, take their derivative, use the definition of the derivative with them. Also, we know that x is an element of the real numbers, which allows us to use all of our fun limit machinery. And we're trying to prove, once again, the chain rule. Alright, so now we're just going to simply state, rephrase this statement, the derivative of f of g of x with respect to x, using the alternate definition of the derivative, which we all know and love so well and may never have learned. But anyway, now that becomes a limit as x approaches c of f of g of x minus f of g of c divided by x minus c, so using the alternate definition of the derivative, the whole thing with respect to x. So now, using those algebra skills that, of course, we have all forgotten, we know that this is the same as the limit as x approaches c of f of g of x minus f of g of c divided by g of x minus g of c times g of x minus g of c divided by x minus c. And of course, you see that the g of x minus g of c and the g of x minus g of c cancel from the numerator to the denominator, leaving us just with this. So now I'm sure you can see where we're going, right? Because this right here, limit as x approaches c, or rather as g of x approaches g of c, should be the alternate definition of the derivative for derivative of f with respect to g, and this piece over here, limit as x approaches c of g of x minus g of c divided by x minus c, is alternate definition of the derivative for g of x with respect to g of c, right? So that's where we're going. There's one little annoyance we have to take care of, though. What happens if we have a rather crazy function like this one? This, I believe, is the graph of x squared sine 1 over x. And if you notice, it oscillates infinitely many times through y equals 0. Now this poses a problem, because what happens if we have g of x equaling g of c in some situation other than than at the point that we're trying to find the limit? And that's what we get when we have infinitely many oscillations. Say, for example, we have c equals 0, we get infinitely many oscillations through 0 as we're trying to get there. So that's a problem, because we'll end up dividing by 0 with this g of x minus g of c. Okay, how do we get around that? Well, let's define a new function, q of y, and we'll plug g of x into q of y. So now we get just this same statement we had up here when g of x is not equal to g of c. Okay, good, we're not getting 0 in the denominator. And now we'll play a trick. Not really a trick, because this is not a problem saying this, and I'll show you why in just a second. When g of x is in fact equal to g of c, we can have a workaround and just say that q of g of x is equal to the derivative of f with respect to g, which is what we want. And the reason we can say this is because if you notice, we're eventually going to we're eventually going to plug this q of g of x into this thing right here, and it becomes this quotient here for f with respect to g. So when g of x is equal to g of c, you notice this numerator right here is equal to 0. So the whole thing will be 0 anyway. So as long as we get rid of this dividing by 0 in the denominator, the whole thing just goes to 0, which is all good. Doesn't matter what we have here in the q. So now we're just plugging that q of g of x into our equation so far, our expression so far. Getting this expression right here, limit is, so now derivative of f of x of f of g of x with respect to x is the limit as x approaches c of q of g of x times g of x minus g of c, all divided by x minus c. So now let's recall again what this expression up here means. So we know that this expression right here is just derivative of f with respect to g, and this, as we talked about earlier, when we take the limit as g of x approaches g of c, which is the same as saying the limit as x approaches c, this expression is just the alternate definition of the derivative of f with respect to g. So we know that no matter what, the limit as x approaches c of q of g of x is just df dg, right? And also, that other expression we had on the second part of our expression, we know that the limit as x approaches c of that is just derivative of g with respect to x, because again, it's just the alternate definition of the derivative that we've all seen so many times, of course. Anyway, so now putting everything together, so remember with these fun facts from the previous slide, we can use the multiplication property of limits, the name I just gave it. I don't know if it has an actual name, but anyway, to distribute the limit, I guess we could say, to the two expressions. So now this, we can plug in this statement that we figured out over here. We get derivative of f of x with respect to g of x. This statement, we plug in the expression we came up with over here on the previous slide. This limit as x approaches c of g of x minus g of c divided by x minus c just becomes the derivative of g of x with respect to x. And now, the magic final step, plug everything in, and we get that the derivative of f of g of x with respect to x is equal to the derivative of the derivative of f of x with respect to g of x times the derivative of g of x with respect to x. That's all, folks. And now, how to identify various types of trees from quite a long way away. The larch. The larch. The larch.